Hi everyone, welcome back bright and early on a Monday morning for MATA02, the magic of numbers. The first thing is I want to make sure this announcement is also recorded, which is we're going back to person in 2 weeks. We're going back to person in 2 weeks, so be prepared for that. I have also built a new chat client, which is the link I keep on dropping in chat, or is the link I keep on dropping in the Zoom chat. So if you go there, voting and chatting there is slightly nicer than on the Zoom chat, because the votes immediately show up, and you can also click on these buttons if you if you don't want to actually type, or you can continue typing. You can also type math in the chat. So for example, if I put can anyone tell you what this link is for? This is the new chat. So if you can also type math in the chat, so like if I type x squared plus 2x plus 1 is equal to x plus 1 squared with $2 signs on either side, you can also type math into the chat. Yeah, so I think that is the big announcement in terms of logistics. I'm building this so that when we go back to in-person, I am able to, continue doing this both in class and lecture, as well as, of course, once we're in person, you can just shout at me and be like, hey, prof, you're going way too fast, slow down. Okay. Any questions about all that before we get started with the class proper? Okay, so let's go ahead and get started. I'll continue making announcements throughout the class, but let's get started. So what are we talking about today? So we are going to be starting on combinations, and what we're going to do today is, we have a question. Assignment do not have a phone or tablet. Oh, the ungraded assignment you don't need to submit. For the actual assignment, you can use your webcam. Just basically anything so that I can read, or I and your TAs can grade your assignment. So if you continue having problems with that, please let me know. Please either put it on Piazza or send an email message, but not right now. So let's get started with class. So we're going to be talking about combinations today. And what are we going to do? Well, let's bake a cake. So what do you have to do in order to bake a cake? Well, you're going to have to measure ingredients, right? And so now I don't know how many of you have baked cakes, but if you've baked a cake, one of the things you've probably used is you've used a bunch of measuring cups, right? So you have a bunch of measuring cups, and you might want to measure out how much of each different thing you're putting in. Maybe if you're putting in flour, maybe you're putting in some egg, maybe you're putting in some sugar, maybe you're putting in some cinnamon, maybe some chocolate, depending on what flavors you want, right? And now, when you're doing this, there are a number of things you can do. So, for example, we have all these different measuring cups, and let me write on this. So this one down here, if I remember correctly, this is the 1 teaspoon cup, a measuring spoon. And then this one here is 2 teaspoons. This one here is 1 tablespoon, which is equal to 3 teaspoons. This one here is 4 teaspoons. This one here is 1/16 of a cup, which is also equal to 3 teaspoons. This one's 1/8 of a cup, and that one's equal to 6 teaspoons. This one here is 1/4 cup, and that's equal to 12 teaspoons. Let's see, then we have 1/3 of a cup, and that's equal to 16 teaspoons. We have half cup, which is equal to 24 teaspoons. We have 2/3 of a cup, which is equal to 32 teaspoons. We have 3/4 of a cup, which is equal to 36 teaspoons. And we have a cup, which is equal to 48 teaspoons. Okay, so there are a bunch of different options we have here for measuring things out. Like you might want to use the cup measure when you're measuring flour, but like maybe when you're measuring vanilla or cinnamon or things like that, then you might want to use one of the smaller measuring spoons, because that's just using up the space. Okay, now I lied. We're not actually going to bake a cake because we're in virtual right now. But let's say we want to, well, I'm using that as an excuse, but let's say we want to measure 5 teaspoons of cinnamon. Now, can we measure 5 teaspoons of cinnamon if we happen... So now, obviously, if you have the 1 teaspoon measuring cup, then you can clearly measure 5 teaspoons of cinnamon. You just take the measuring cup and do it 5 times, right? So that's not too hard. But can you do it if you have the 2 teaspoon cup? So this one right here, if you have these two. The 2 teaspoon cup and the 1 tablespoon cup. So, yes or no? Let's do this. Let's zero out the chat and just yes or no. Can we do this? Like, this would be pretty easy. Any of you who've baked cakes. Oh yeah. Can you please put the for the votes? Do you mind putting the votes in the other one? So only vote in the other one that shows up. So, which I've just put a link to in the chat. So please go over there to vote and don't vote in the Zoom chat. Yeah. So again, I'm putting in the link in the chat. Please vote over there. Okay, so it looks like this one is pretty easy. Well, obviously this is easy. 2 teaspoons plus 3 teaspoons is equal to 5 teaspoons. Right? Okay, easy enough. But now, what about 1 tablespoon and a 1/3 cup? So can you measure out 5 teaspoons of cinnamon if you have 1 tablespoon and a 1/3 of a cup, and that's it? Now remember, when you're doing this, you can measure in 1 cup and then like subtract out by using the other teaspoon using your tablespoon to like remove stuff from the cup, and so on. So can you do this? Is this one of those cases where you can do it in... so now, this is where we sort of leave the realm of the actually baking. So this is where we leave the realm of actually baking and switch over into the realm of theoretical baking. So can you do this in theory? If you have a 1 tablespoon, which is 3 teaspoons, and a 1/3 of a cup, which is 16 teaspoons, can you somehow combine the 2 of those together to get 5 teaspoons? Okay, so we have a reasonable number of votes. So the votes are still trickling in. Remember, vote over in the new chat. So the answer to this is, well, yes, in theory. I mean, the mathematical answer is yes, but so what do we do? There are a couple different ways you could do this. So let's start by measuring 2 1/3 cups. So that's equal to 32 teaspoons. And then let's remove 3 teaspoons 9 times, which is equal to minus 27 teaspoons, because we're removing it. And what are we left with? Left with 5 teaspoons. Okay, so, well, I mean, like I said, this is theoretical baking now, because if you were to actually do this, it probably wouldn't be very accurate, since you wouldn't be exactly right at removing a tablespoon each time. But, in theory, you can do this. Okay, well, let me zero out again. What about if you have a 4 teaspoon spoon and a 1 cup, so which is 48 teaspoon cup? So, in that case, having this one here and this one here. So, what do people think? Let's see. So again, you have to really think about this one. Can you create 5 teaspoons from a combination of 48 teaspoons and 4 teaspoons? So we just showed that you can do that with 3 and 16. Can you do that with 4 and 48? Okay, so it looks like people are a little bit more divided here, but people think it's probably no. So like somehow we can do it with 3 and 16, but not with 4 and 18. 4 and 48. Does anyone want to guess as to why? So the answer here is indeed no, but why? Why can you make it, okay, so it looks like Niraja, yes, we have a couple different replies. They're both even numbers, and so you can't ever get an odd number like 5. Exactly. So that gets you at the heart of it. So this doesn't always work exactly, but like that is a very good heuristic for why you can't get 5 from 4 and 48. Okay, so let's keep on going. So this was all about baking, right? So now let's play a video game instead. So let's suppose we're playing a video game. So this is the video game Hades, which is a fairly recent game. But in some video games, you can either move normally or you can do a fixed length dash. So you can, and also, when playing with a keyboard, a single button press might be go a specific distance. And so now if you're playing with a controller, those often have an analog stick that goes some continuous amount. But when you're playing with a keyboard, a single button press might go a specific distance. So now, if we have a particularly fast dash, and we have a slow single walking step, so if, say, the dash goes 9 feet, and walking goes 2 feet, can you go exactly 25 feet? Let me zero out the poll. Yeah, so can you go exactly 25 feet? Okay, yeah. So we have most people saying yes. One or two people, I think, said yes, but only in theory. But remember, this is now a video game, not real life, and so it's actually easier to do these sorts of exact summations. Well, let's take a look at how we do this. So one way to do this is 9 plus 9 plus 9. So if you do 3 dashes in a row and then take a step back, then that gets you 25, because that's 27 minus 2, that's 25. Or if you wanted to go the slow pedestrian way, maybe you walk 8 steps, 2 plus 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 2, which is equal to 16. And then you dash, 16. And then you dash, which is also 20. So that was 27 minus 2, or you could have 16 plus 9, which is also equal to 25. A reminder to everyone, please go over to this website and do your voting there. So that's where we're going to be doing voting from now on. Okay, so that's good, right? But what if, so in some video games, you can speed up your walking speed. So what happens if you speed up your walking speed to go 3 feet? Let me zero out. So if you speed up your walking to go 3 feet, but your dash still goes 9 feet, can you now go exactly 25 feet? So what do people think about this? Okay, so it looks like we're getting a lot of B's. So we're getting people that are thinking, oh, well, this is, some people think only in theory, but a lot of people think that the answer here is no. But why is the answer no? Anyone want to give a guess? So in the previous one, we guessed because that's something about divisibility. So we have the answer from Tiffany. There's no way with that combination of 9 and 3. There's no combination that can be 25. Well, yes, that's true, but why is there no... 9 and 3 are multiples of each other. Okay, so that's getting at the right sort of answer. It turns out both 9 and 3 are multiples of 3. And 27 isn't a multiple of 3. And that's the reason why. It's because we notice anytime you do these, if you have 9 and 3, anytime you do steps, whether it's addition or subtraction, as Tristan says, there's no fractions, and therefore you can't actually go anything that's not a multiple of 3. So the answer to this is no. can only go multiples of 3. So sometimes we can go all these different distances, but other times you can't, or you have some restricted set of distances you can go. And this is really at the heart of what we're going to call combinations. So that's the topic of today's lecture. So given two integers a and b, so given two numbers, the sum of a multiple of a and the sum of a multiple of b, if you allow for negative multiples, is called a combination of a and b. You can think of this as, mathematically as a plus x a times x plus b times x, where x and y are both integers. So as an example, maybe if a is equal to 17 and b is equal to 7, then 11 times 2 plus 7 times 3, which is equal to 43, is a combo of 11 and 7. Right? And this is exactly the sort of problem we just had with both baking a cake using weird measuring cups if you had lost most of yours, or in video games if you have particular movements that get you a certain number of steps versus other movements. And so these are combinations. Obviously, if you have 1 as one of your things, then you can get any number because you can just do 1 that many times. But if you have other numbers, asking what numbers are combinations, so what types of steps can you take? What types of distances can you go? And also, if we know that n is a combination of a and b, so if you know some number is a combination of a and b, how do you find multiples of a and b that actually add up to n? So for example, if I just told you that 43 is equal to 11x plus 7y, how do you find x and y as integers? So obviously, if you had fractions, you could just divide, and you can get lots of different solutions to this. But if you don't have fractions, how do you find x and y as integers? So there are a number of ways you could do this, and one of them is through creating unity. So 1 is the unity, and one thing you can do is, if you figure out how to go a single step, if you figure out how to go exactly 1 step, then you can, in theory, figure out how to go any whole number of steps just by repeating that procedure, repeating the whole procedure over and over again. So, for example, if you have 1 tablespoon and a third cup, so going back to our baking example, well then we know how to measure 1 teaspoon. 1 teaspoon is actually just exactly equal to 16 teaspoons minus 3 teaspoons times 5, right? So if you take a single tablespoon and just remove 5 teaspoons from it, then you're left with a single teaspoon. And so now we know how to get exactly 1 teaspoon's worth of cinnamon or vanilla or whatever you care about. And then what you can do is you can just repeat that any number of times, showing that we can make any number as a combination. So for example, if we wanted 5 teaspoons, that's just equal to 5 times the 16 teaspoons minus 3 teaspoons times 5. Right? So that's equal to 5 times 16 teaspoons, which is 80 teaspoons. Oh, sorry, I should leave it as 5 times 16. 5 times 16 teaspoons minus 3 teaspoons times 25. And this, of course, is 80 minus 75. We have a question. Are combinations with decimals allowed? So no, for the purposes of today's lecture, and for we're only allowing for integer combinations. So where these are just exact multiples. So we're only allowing these to be integers. Now, if you allowed to have decimals, then you could do really anything you wanted, really. So this is the case where you only have a whole number of measurings. So like, if you only have a tablespoon and a third of a cup, then even though you could sort of eyeball a half tablespoon, you can't really measure a half tablespoon. Okay, so now you notice that we actually gave a different solution here, because earlier we gave the solution that 2 times 16 minus 3 times 9, whereas this one here is was 32 minus 27. Whereas this time here we gave a different answer. Oh, wait, did I do that wrong? Wait, shouldn't it be 15? No, I don't think it... Oh, wait. Oh, I see where the confusion is. Let me rewrite this to make it a little bit more clear what we're doing here. So here, this is 16 teaspoons times 5, right? Minus, distributed properly, 3 teaspoons times 5 times 5. So that's equal to 16 teaspoons times 5 minus 3 teaspoons times 25, which is 80 minus 75. Does that answer your question? Okay, so now what we figured out is if you can make one step, then you can make any number of steps, because you can just repeat that process. It might be less efficient, but we're mathematicians, and so in theory, that's something you can do, and things will turn out all right. But now, that of course raises the question, how do we make smaller combos? So, I mean, if you happen to know how to make one, then you're done, but if you don't know how to make one yet, let's say you start with 2 really big numbers, can you always make one? And we know that sometimes you can't. So what's the smallest combo you can make? Well, let's say that we want to make combinations of 35 and 100. So one thing you could do is, well, I mean, if you have 35 from 100, maybe you can repeatedly subtract 35 from 100 to get a smaller combo. So let's say 100 minus 35 is equal to 65. Well, it doesn't really help yet because we already have a smaller combo, 35. So let's do it again. So 65 minus 35, so basically taking two steps of size 35 back, well, that's equal to 30. And 30 is actually smaller than 35, and so we've now successfully made a smaller combo. Okay, so that's good, right? Well, let's rewrite this slightly differently. You can also write this as division with remainder, since multiple subtractions is just division with remainder. So 100 divided by 35 is equal to 2 remainder 30. So that means that 30 is equal to 100 minus 35 times 2. Yeah. Okay, so we can rewrite it in that way. And, well, now we know how to make 30, and so we can use that as a building block, and then do it again. So maybe we want to make something even smaller. So, well, we know how to make 35, that's one of our basic steps, and we know how to make 30. So 35 minus 30 is equal to 5. So we know that 5 is equal to 35 minus 30, but we know how to make 30, so 30 is equal to 100 minus 35 times 2, right? So that's equal to, when you do the distributive property and figure all of this out, that's going to be 35 times 3 minus 100. So what we've just done is we just invented a way to move 5 steps by moving 3 steps of 35 first, and then going backwards by 100. So now the issue now is we're stuck at 5, since 30 divided by 5 is equal to 6, and so even if you keep on trying to go down, 30 to 25 to 20 to 15, 10 to 5, the next jump goes straight to 0. And so we're stuck at 5 and we can't actually get smaller. And so the smallest step we know how to make, the smallest combo we know how to make is 5. Okay, so now does this remind you all of anything? So does this remind you of anything we've learned before? This process of like making things repeatedly smaller. Anyone in chat? Long division, factoring. Obviously we are doing division, but what about the sort of repeat? Oh, okay, so we have, yes. So we have people who've answered in chat that we are interested in the Euclidean algorithm. Yes, that is exactly what we're doing. So it turns out that if we start with 2 whole numbers, a and b, so for example, let's start with 2 small ones here, just to make life easier, 6 and 4, then we can divide a into b, let r be the remainder. If r equals 0, we're done. A divides b, and we find the greatest common divisor. And if r is not equal to 0, then we replace a and b with r and a and repeat. And this is just the Euclidean algorithm. And so the smallest combo we can make is precisely the greatest common divisor. So in this case, this is a super easy example. 6 divided by 4 is equal to 1, remainder 2. And 4 divided by 2 is equal to 2. So 2 is equal to the greatest common divisor of 6 and 4. And now, that means that, of course, we know how to make any multiple of 4, right? Or sorry, of 2, of the greatest common divisor. So if you have a goal of 10, which is divisible by 2, well, you know 2 is equal to 6 minus 4. And so if you multiply everything by 5, if you repeat this 5 times, if you go 6 and then back for 5 times, then you get 5 times 2 is equal to 5 times 6 minus 5 times 4. And so therefore, you know 10 is equal to 5 times 6 minus 5 times 4. And importantly, this is not the only way. But this is one way of doing it. Not the only way. Way to make 10. Because, of course, you could also do just 6 plus 4. But you don't necessarily, so if you're clever, you can look at this and be like, well, 6 plus 4 is 10, and then you're done. But even if you're not very clever, you can still use the Euclidean algorithm to figure out how to make 2. And then once you know how to make 2, then you just make 2 5 times, and it gives you 10. Okay, so what about other combinations? Can you make positive numbers that aren't multiples of the greatest common divisor? So notice that we have this method for making numbers that are multiples of the greatest common divisor, but we can also make numbers in other ways. So these other methods that you use, can you use them to make numbers that are not multiples of the greatest common divisor? So really think about this a little bit. And even though I just showed you how to make multiples, let's go back and think about what happened in the very first examples. So when you had the video game example of 9 and 3, Zagreus could only move in multiples of 3. So in this case, can you make numbers that are not multiples of the greatest common divisor? Or is that all you can do? Okay, so we have a lot of people who are guessing that yes, you can make other positive numbers that are not the multiple. Unfortunately, that turns out to be wrong. So, no, you cannot. Why is this the case? So now, I just suggested that you can make all the multiples, and what we need to show is that that's all you can do. Now, if you think back to the examples we did earlier of either Zagreus moving 9 and 3 steps, in which case you can only go multiples of 3, or if you have 4 teaspoons and 48 teaspoons, it turns out that you can only go multiples of 4. Why is that? Oh wait, where was I? Process of making smaller combos, other combinations. And there's a very deep mathematical reason for this. So let's actually prove this. And by proof, all I mean is an argument. A proof is just a mathematical argument. So what are we arguing? So, well, let's let D be the greatest common divisor. So we're just renaming that to make life easier. So if it's the greatest common divisor, then that means A is equal to M times D, and B is equal to N times D, where M and N are integers, right? So that's what it means to be the greatest common divisor. So then any combination is then x times A plus y times B, where x and y are integers. But then what's that equal to? Well, that's equal to x times M times D plus y times N times D, where x and y are integers. And if we use the distributive property and factor out, then that gives you x times M plus y times N times D. But now, of course, everything we're working with is integers, and so this here is a whole number. And so this entire thing is a multiple of D. And therefore, anything you can make has to be a multiple of the greatest common divisor. So the set of combos of A and B is precisely the multiples of the greatest common divisor. And this is always the case. So once you have the greatest common divisor, then you know all of the possible things you can create. And this is the reason why when we were measuring ingredients, if you have 4 and 48, then the biggest thing you could make, the smallest thing you can make is 4, and you can only make multiples of 4. Whereas if you have 3 and 16, the greatest common divisor there is 1, and so you can make any number you want. And the same case for the example of Zagreus and Hades. So if you have 9 and 2, well, you can make 1, and so you can make any number. But if you have 9 and 3, you can only make multiples of 3. Do we have any questions about that? Okay, so no questions. Let's have you try it out. What is the set of combinations of 36 and 3222? Will you ever have to do proofs like that? So I don't want to say you'll never have to do them, but certainly not yet. Can you go back to the last slide for a second? Yes. Okay, well, let's give people a moment, since this is suddenly some of you have already learned the Euclidean algorithm. I know that because I went through all of the ungraded original CrowdMark set, and I looked at all your answers, and some people like just jumped ahead and did the Euclidean algorithm on their sheet. Also, some people drew really, really nice things, and so I am jealous of all your art skills. And I also made comments. So if you guys turned in something for the ungraded CrowdMark test at the very beginning, I made some comments and I responded to all your things. They're just the short one-sentence comments, but yeah, just FYI. Okay, so we're getting a lot of guesses for B, and let's wait another moment, and let's give people a little bit longer to figure this out, and then we'll go back and do it together. Okay, so we're getting a few A's, a bunch of B's, and a C. Well, let's try this out now. So what's a combination of 36 and 3222? Well, what we want to do is we want to divide, right? So let's say we want to divide 3222 by 36. So what is this? Well, let's say that's an 8 there, but that gives us 288. So you should actually do this. 36 times 8 is 288. Subtract that out, you get 334. Carry the 2 down, and then that's the biggest multiple of that divides in is 9, so 324, and the remainder is 18. Okay, and so what this means is that 3,222 is equal to 36 times 89 plus 18. And we also know that 36 is equal to 18 times 2. And so therefore, 36 and 18 have the same, there's a divisible. And so the greatest common divisor of 3,222 and 36 is equal to 18. And therefore, the answer is actually B here, so multiples of 18. Okay, so that's easy enough. Well, let's go back to why did we come up with greatest common divisors in the first place? That had something to do with least common multiples, right? So let's try that out since we didn't have time to do this last time. What's the least common multiple of 36 and 3,222? Okay, so we're getting a couple of different guesses. Let me wait a moment and see if anyone... Okay, so B is starting to pull ahead a little bit, but C and E are pretty close. So, remember, if you have A and B, one of the important facts that you should know is that A times B, if these are numbers, is equal to the greatest common divisor of A and B times the least common multiple of A and B. So that's a fact that we proved in the last lecture. Okay, so it looks like we have a quorum, we have a majority for B, and well, let's see what happens. So, well, we know the greatest common divisor of 3,222 and 16 is equal to, 36 is equal to 18. And so, therefore, the least common multiple of 36 and 3,222 is equal to 36 times 3,222 divided by 18. So it would be a little bit of work to actually do this all by hand, to multiply out 36 by 3,222 and then divide it all by 18. But luckily, we can do this a slightly easier way, which is this is equal to 36 divided by 18 times 3,222. And so that's equal to 2 times 3,222, which is equal to 6,444, which is again B. I think I've chosen B a number of times here. Okay, so that's a reminder from last lecture. So you should know how to do that. I think it's on one of your homework assignments. And let's try another one. So we know the greatest common divisor, and so we know how to work with that. What if I want to find integers? I want to find integers x and y such that 36x plus 3,222y is equal to 9. So what we're trying to do now is we're trying to make a combo. So if you're able to step 36 steps or 3,222, a super giant leap, can you ever step exactly 9 steps? 9 feet or 9 meters or 9 teaspoons or whatever you want. So we have a guess of no. So if your guess is no, it should be none of the above, right? So. Okay, so we have some people guessing B. And we have some people... what is B? Oh, blah, 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 blah. Sorry, the choices aren't up. Yep. The choices are now visible. I guess some people are following along in the, yeah, so they should be visible now. I guess some people are following along in the PDF that I provided before class, and so that's how they were guessing. So apologies for that. So, which of these do you think it is? Okay, so it looks like we have a bunch of guesses. Most of them are for B, a couple E's, and one D. So, I'm going to solve this problem. I'm going to solve it one way, but then I'm going to point out that there's another thing you should have done to check. So, the first thing is, recall, since I'm using the same numbers over and over again, the greatest common divisor of 36 and 3,222 is equal to 18. So only multiples of 18 are possible. So 9 is not possible. Now, a lot of you guessed B. But now, remember, when we talked about how do you solve a problem in the last lecture, right? So, how do you solve it? Well, one of the things that you should do is once you've guessed an answer, well, sometimes it's useful to double check whether your answer was right. So now, for example, what happens if we guessed B, which a lot of you all did? Well, then, one way you can double check is just plug in those numbers back in and see if the things work out. So, 36 times 89 plus 3,222. Is that equal to 9? So if you figure this out, you'll notice that all these are positive numbers and they're bigger than 9, and so this is not equal to 9. And so even if you manage to get the answer B somehow, you should still double check your answer and be like, well, if I multiply them back in, do you get the answer that you want? And in this case, you very clearly don't. Okay, let's keep on trying this out. What if, and let me put them back up, can you make 18? If you can, how do you do it? Okay, it looks like people are trickling in some answers. Let me remind you of what the work we did for the Euclidean algorithm. So let me remind you that 3222 is equal to 36 times 89 plus 18, and 36 is equal to 18 times 2. And this was the Euclidean algorithm. Okay, and therefore we know that 18 is equal to 3,222 minus 36 times 89. And so therefore we have x is equal to, oh sorry, not 98. Why did I put 98? 89. Let me use the other times symbol just so that the x doesn't get confused. Times, times, and times. So x is here is going to be equal to minus 89, and y is equal to 1. And so that, of course, is C here. Okay, good. So let's try out yet another one, because this is important. And if I posted the practice quiz via CrowdMark yesterday, and so you'll notice that one of the big problems on CrowdMark is one of the questions that's on your practice quiz is using the Euclidean algorithm. As I mentioned, the practice quiz looks very, very much like your actual quizzes, and so make sure you know the Euclidean algorithm. And make sure you know how to show your work as well. So let's try it out for a slightly different one. What about 36? So if you know how to make 18, can you make 36? So, okay, so we're getting a decent number of, starting to get replies trickling in. So let's remind you all of what we know. So we know that 18 is equal to 3,222 minus 36 times 89. And this implies that 36 is equal to 2 times 3,222 minus 36 times 178. And so here, y is equal to 2. Actually, let me do that in the other order. So obviously you can do it in either order, but it'll make life easier if you do it in this order. 3,222 times 2 minus 36 times 178. And so then x is equal to minus 178, which is D. So note that this isn't always the most efficient method, right? So as an aside, there's another solution, right? So there's another really simple solution, which is x is equal to 1 and y is equal to 0. But that's not the solution we get from the Euclidean algorithm. So the Euclidean algorithm doesn't always get you the easiest solution, but it will give you a solution. Okay, let's do another one. What about 45? Let me zero out the chat. So what about 45? Okay, yeah, so this one should be straightforward because we can recall that greatest common divisor of 36 and 3,222 is equal to 18, and 45 divided by 18 is equal to 2 remainder 9, so not a multiple of 18, so not possible. Okay, let's see. And in the final remaining time, final couple minutes, I'm going to do a more complicated example. So, because you'll be seeing more complicated examples in your tutorial as well as on the problem set and the practice and on the practice quiz. So let's do 133 and 26. And I'm going to walk through all the steps, and then we're going to finish here. I had two complicated examples, but I'll put the other one on the notes later. So let's start. 133 divided by 26 is equal to 5 remainder 3. And so another way of writing that is 133 is equal to 26 times 5 plus 3. But if we continue doing the Euclidean algorithm, 26 divided by 3 is equal to 8 remainder 2, or 26 is equal to 3 times 8 plus 2. And we also have 3 divided by 2 is equal to 1 remainder 1, or 3 is equal to 2 times 1 plus 1. And we have 2 divided by 1 is equal to 2, so that's divisible, and our Euclidean algorithm ends. And we know that the greatest common divisor of 133 and 26 is equal to 1. Okay, so now, how do we create 1? Well, you can rewrite all these equations. 3 is equal to 133 minus 26 times 5. We also know that 2 is equal to 26 minus 3 times 8. And we know 1 is equal to 3 minus 2. And so if we go down from this, what you get is 1 is equal to 3 minus 2, but then we can substitute. So 1 is equal to, and whenever you substitute, you want to substitute in the smallest thing first. 1 is equal to 26 minus 3 times 8. So therefore, 1 is equal to 3 times 9 minus 26, because we have 8 copies in 1, and we add those together. And then you can substitute in for 3. So then 1 is equal to 133 minus 26 times 5 times 9 minus 26. And so you're left with 1 is equal to 133 times 9 minus 26 times 46. Okay, so that allows us to create 1. If we wanted to, we could do things like create, say, 3. So you could also say that 3 is equal to 133 times 27 minus 16 times 138. But of course, there are two different ways of making 3. But this would be this way here would be the way using the Euclidean algorithm to show that you can solve it, even if it's not necessarily the nicest solution. Okay, and with that, I will not put the other example. So if you want another example to play with, you can try doing 2022 and 133, which is the number of people registered for this class. But we're not going to do that because I am out of time. So thank you all very much. Hope all of that worked out, and I will end the recording here.